Okay, so this is a lesson about, remember I told you I was going to change our whole number system. So this lesson is about imaginary roots and complex numbers, and I know you don't know what those are, but just hang in there. Okay, so suppose I ask you this question: find the x-intercepts of this quadratic. If we tried, to find the x-intercepts, we're going to plug in 0, right? If we tried to do this quickly by factoring, we would have x and x as our combinations, 1 and 2 as our combinations for our constant. It would be a sum table, and we would sum to be 3. So this won't work. So we can't factor, so our only option is to do quadratic formula. So I went ahead and plugged into that, okay? But with this one, if we focus on right here in the inside, our 2 squared is going to be 4. And then 4 times 1 times 2 will be 8. So we've got 4 minus 8 inside of there, right? And 4 minus 8 then would be a negative 4. And if you remember back from Algebra 1, at that point we would have said this type of equation has no solution because you can't square root a negative number. Your calculator will tell you error. You won't be able to do it. So what does that mean as far as our graph goes? So I went ahead and I wanted to graph this. So to graph in standard form, remember we have to find the intercept by doing opposite of b over 2a, then plug that in. So here is my opposite of b over 2a. So for my x I got negative 1, then I plugged that in for y. I got out positive 1, so I know my turning point is at negative 1, 1. And my rate of change is double my a value. So since my a value is 1, my rate of change is changing by positive 2, right? So let me get rid of that guy. Let's go ahead and graph this then. So our turning point's at negative 1, 1, that's here. Our rate of change is changing by 2, but first I've got to get my first stair step in there. My a value is 1, so my first stair step is 1. And I'm changing by 2, so my next stair step will be 3. And then the next stair step will be 5, right? So I'll be up here. So my quadratic looks something like this. But remember I had asked originally to find the x-intercepts of this quadratic. Well, check out the x-axis. Are we ever going to be crossing the x-axis? And that answer is no, because we're above the x-axis. That's why we're getting a no solution. That's why we're getting a negative. It tells us that we're not crossing the x-axis. But what I want to get into today is, why not just expand our number system so that we can include roots of negative numbers? Why not? You know, invent some new numbers. I mean, really, aren't all numbers invented? It's not like they grow on trees. Humanity just made them up. So why don't we make up a number or some numbers where we can take roots of negatives? As long as it works with our rules of algebra and of math, it should be fine. So somebody's done this already, of course. And this isn't so alarming. It's really just one new number. And that one new number we call the imaginary unit. We call it the letter I. Now this is not a variable. I is not a variable, not like x. I represents a number, just like pi represents a number. Pi is not really a variable, it represents a number. I represents a number, and it represents the square root of negative 1, which, as far as you knew up to now, didn't exist. But we're going to say, yeah, it does exist. We're going to call it I. Okay, hang with me for a minute. Then all we're going to do is redefine every number that we already know. So all of our existing numbers, we're going to redefine with this new component. Let me show you what I mean. So every number you know now, for example, you know the number 3, you know the number negative 76, you know the number 6.1325. All of these numbers that you know now are really what we call complex numbers made up of 2 components. And those 2 components are, there's a real component and an imaginary component. It's just that you've only ever focused on the real component. You've never focused on the imaginary component. And that's because each one of these numbers When I add on its imaginary component, it has 0 imaginary component. These are normal numbers too. They're not imaginary at all. So they have an imaginary component of 0. So it's just that you only knew about the numbers with no imaginary components. And what we're going to talk about today are numbers that have real components and imaginary components. And you never knew about those. So it's kind of unfair that you only knew about the complex numbers that had real components only. So let's look back at that quadratic, where this is where we had stopped and we said no solution, right? So if we kind of play with this root -4, so let's use this idea. So if I have, I'm going to write this off to the side, square root of -4. Couldn't I rewrite that as -1 times 4, right? And really each of those could have its own root. So that could be like, let me give myself some space over here. That could be like root -1 and a root 4, right? That's what we talked about, breaking things apart inside of roots in order to reduce. And now you know that the square root of -1 is I, and the square root of 4 is 2, and the operation between these things is times when they're next to each other. It's just normally we don't write a letter before a number. We would really call this 2i. So the square root of -4 is very similar to the square root of 4. It's just it has an imaginary component with it. So what I did was I showed that work, except here I wrote the 4 first and the root -1 second, not that it really matters, so that we could easily see why it's 2i. Square root of 4 is 2, square root of -1 is I. And then we'll just treat it like normal. So split it apart and reduce, right? So if you split that apart and reduce, you get -1 plus or minus I, because 2 over 2 is 1, right? You could put the 1 in front of the I if you wanted. So we're getting that we have our x-intercepts there aren't any real x-intercepts. We have 2 imaginary x-intercepts. One when x is at -1 plus I, and one when x is at -1 minus I. Now, this is like kind of confusing. Let me pull up our graph again. So we're saying we don't have roots that are real roots. We have what we call imaginary roots, but what does that look like? Because on our graph, we very clearly don't see any roots. So where do we see imaginary roots at? How do we know if we're right when we get these imaginary roots? What does that mean? What does it look like? So I want you to pause for a second and think about the coordinate plane as you know it. The coordinate plane as you know it goes x-axis, y-axis, right? Right? We also have what's called, instead of just a regular coordinate plane, we have what's called a complex coordinate plane, where this is called the real axis, and this is the imaginary axis up here. So let's say I wanted to plot a complex number. So let me get you a complex number. Remember, complex numbers are where we show the real component and the imaginary component. So let's say we have the complex number of 3, and maybe it has, not plus minus, let's just do 1. 3 plus, and it has an imaginary component of 2i. So the real component is the 3, that's the real component. And then the 2i is the imaginary component. So the way that we're going to graph this is, again, the real axis is the one that's going horizontal. This is our real axis. The imaginary axis is here. So you can almost put eyes with all of these to kind of help you out. Okay, so if I want to graph 3, I come over to 3 on my real, and then I go up to positive 2i. So here is the number 3 plus 2i. Okay? Let's graph another one just to practice at it. Let's say I wanted to graph -4 minus I. So my real component, my x, kind of like if you want to think about it, is back at -4, and then minus I, that's minus 1i, so I'm down right here. This is the spot, -4 minus I. Okay, just one more just to practice. Let's say I've got 1 plus 5i. No, let's go 1 minus 5i. So my real component is 1, so I'm going to go over to 1. And then my imaginary component is minus 5, so that's all the way down here. So this is the number 1 minus 5i. Okay? So let's use this idea of, we already have our normal xy coordinate plane, but now we know kind of what a complex coordinate plane looks like. So let me take our graph again. So this is our graph of our function that we've been working with. Remember, it does not cross the x-axis, so we didn't see our real roots. And I just kind of zoomed in on it. I zoomed in so we could really focus right down there. Okay, what we got as our imaginary roots were, remember we split this apart, that was -1 plus I and 1 minus I, oop, -1. Sorry about the announcements. But I'm gonna keep going. So, if I plotted those points, actually I'm going to wait to plot those points. Imagine reflecting this graph really quickly. Reflect it upside down. So I'm still going to keep this guy. If I reflect it upside down, I've got my points here, and it kind of looks like this, right? If I reflect it upside down. Okay? Now, I want you to think about, where is this imaginary number if I plot it, and where is this imaginary number if I plot it? So, thinking of our y-axis as our imaginary axis, I'm going to put i's next to those for a minute just to remind us. -1 plus I means go back 1, and plus I would put me right here. And -1 minus I, back 1, and down 1 puts me right here. So what you find, and this always happens, it's kind of really neat, that if you take your quadratic, reflect it upside down, and plot your imaginary roots, you always make a circle. It's just kind of cool. Let me show you another one. So again, we reflected it upside down and looked at our imaginary roots with what our roots would be if it was reflected. It always makes a circle. Let's try another one so you can see this again. Okay, so find the x-intercepts. I'll just tell you right now, this is not factorable when we try and find them. So might as well go straight to the quadratic formula. And then again, I focused here on the inside, worked that out. We've got 64 minus 80, which we know is going to be negative. Okay, remember you can think of -16. We could rewrite that as 16 times a -1. And we know the square root of 16 is 4. The square root of -1, that's our new number, I. So I can write this as 4i. Split it apart and reduce. And we should get 2 plus or minus 1i. Okay, so let's check this out and see what this looks like. So it's in standard form, so I need to get the vertex, I need to do opposite of b over 2a. So I did that over here. Here's my opposite of b over 2a. Got out 2. So far I know my ordered pair starts with the 2 of my vertex. Now I need to plug that in to get y. So I did. Oops. Plugged that in and got 2 out for y, which tells me that my vertex is at 2, 2. And then since our a value was 2, we know our rate of change is changing by 4. So let me plot that real quick. 2, 2 is right here. Our a value is 2, so our first stair step is 2. And then we know we're changing by 4. So I should be 6 at my next spot, which will put me up here. So if you just look at this, you can see why we were getting a negative inside the square root. We have no real x-intercepts. We're above the x-axis, right? So we don't have any real x-intercepts, but we do have imaginary ones. So again, let's look at what that looks like. How do we see that on the graph? So reflect your quadratic upside down. So keep that. Our 2 points were 2 away, and then our next ones were 6 away. So actually 1 down here. I'll just kind of make that dotted. This is our reflection. Okay, and then if we plot our intercepts, our imaginary intercepts, so this is x equals 2 plus 1i and x equals 2 minus 1i.
Julia, Lee, Matt Fowler, Jen Welby, France.
So again, go to your axis. Think of the y-axis as imaginary numbers now.
Grace Miller, Sarah.
Right? So our x is our real, our y is our imaginary. And let's plot those two intercepts. 2 plus 1i means go over 2 and up
celebrating their birthdays today and
1.
Saturday. Chandler Clem, Nick Clem, Kelly Douglas.
Then 2 minus 1i says go over 2 minus 1. And check this out. There is our circle. Again, made between what our roots would be if we flipped it upside down and our imaginary roots. That always works. That's how you'll know you're right. Okay? Now you may be asking why? Why would we make something up? Why would we make up imaginary numbers? And actually, that's a great question. At the time that somebody said, hey, why don't we do this just to see? Everybody thought this would be kind of pointless. Why would we need this? There's going to be no application. And that's why they were called imaginary numbers, because there was no, it didn't seem like there was any real world application. But what we know now is that there are a lot. These are just two examples. Electricity is one. So electricity, those are electricity waves are usually sine waves. And what we're seeing is if you combine, that's this, if you combine two AC currents, alternating currents, it can be hard to figure out what the new current is. Mathematically, it's hard to calculate. But if you use imaginary numbers, it becomes a lot easier to do the calculations to figure out what the new current is. And even though you're using imaginary numbers to do calculations, you're still coming up with a real current as the combined current. So even though it feels like it's imaginary current, because you're working with imaginary numbers, those are real things. And that new current can still hurt you. It still exists. You just calculate it using imaginary numbers. Another place that uses imaginary numbers is control theory. An example of, just a quick, easy example of control theory is your car's cruise control. That's where you kind of try and lock your car at a certain speed. The throttle is what tells your car, or how much, it tells your car really how fast to go. I mean, how much power are you sending to your engine? So if we were doing a very elementary thing, we would just like lock our throttle into position. But if you just lock the throttle in a single position,
And Marlette, please come to the main office.
You would only maintain that speed if you were on a flat surface. If you start going uphill or downhill, if your throttle is locked, it's not going to take into effect that gravity is pulling you down if you're going downhill. So suddenly you're going to be going faster even though you're locked in a throttle position. Gravity's pulling you faster, or uphill slower, which you don't want. That's not what we want. We want our car to actually stay the same speed, not the same throttle position. So your car is a system that monitors speed changes and adjusts the throttle position when it's going uphill or when it's going downhill. And that's control theory, like when things are kind of oscillating around a speed. Or not necessarily a speed, kind of like temperature, kind of like keeping a temperature in a room. But when things oscillate around a number. Control theory, if we do a little bit more complex systems than what we're just talking about with cruise control, you use complex numbers and imaginary numbers to tell if the system is stable or unstable. So if that oscillating is stable or unstable. So those are just two examples. But anyway, so this is just an introduction to imaginary numbers. Remember, they come from square rooting a -1, and that's called the imaginary unit. And every number you know really is a complex number. It has a real component and it has an imaginary component. It's just the numbers that you know had no imaginary component. Now we're going to look at numbers that have both components.